By the way, I did calculate the kinetic energy for that is being absorbed by the cannon that's bolted to the Earth. First, I did the final velocity, the recoil velocity, and I come up with like 10 to the negative 21 meters per second. So a tiny amount, obviously, because it's a huge mass for the Earth. And then for this kinetic energy here that I assume to be 0, well, truly enough, I come up with 10 to the negative 16 joules. So the cannonball gets 10 to the 6, or actually 10 to the 7 joules, while the Earth, or the cannon that is bolted to the Earth, gets 10 to the negative 16 joules. So that justifies what I said earlier, that that is negligible amount. Okay, what are we going to do with what we have so far? Well, we're going to use that, and we're going to unbolt the cannon now. Again, I may want to take this out of here. And now for the unbolted cannon, I basically do the same algebra, so it's going to be 0 before anything happens times m1 vf1 plus m2 vf2. And then for the energy, it's the same amount of energy, so the 12.9 times 10 to the 6 joules. But now with the cannon being unbolted, that second term that I write down in just a moment is perhaps not negligible. Because now the cannon's mass at only in quotes 5,000 kilograms is a whole lot smaller than the Earth's mass. So that means that the recoil velocity is not in the neighborhood of, like, what did I have a moment ago, 10 to the negative 21, but it's going to be in the neighborhood like a few meters per second or so. And that's appreciably enough that it does absorb some of the energy from the gunpowder, and that also means that it takes energy away from the cannonball, because this is the same amount here, 12.9 times 10 to the 6. If some of it goes now into the cannon itself, then the cannonball has less energy and therefore also less momentum and less velocity. Okay, as far as the algebra goes, what I have so far here is that I have two equations with two variables. I don't know what VF1 is, and I don't know what VF2 is, and this is what I have to figure out. How do I do that? Well, I take the first equation and solve for VF2 and substitute in the second one, and then the only variable that's left is the final velocity of the cannonball. And so that's what I'm going to do here. I may need, well, I'll see how much space I need. So Q is not a variable at this point because we calculated it earlier. So this one here is Q equals 1/2 mVF squared, same term, and then plus 1/2 m2. And now this one here being solved is going to be a negative m1 over m2 vf squared. So that's what I'm going to write down. Negative m1 over m2, and then I think I said a moment ago vf squared. That's not what I meant. I meant vf1, close the parentheses, and then because I substituted in here for the vf2, the square is on the outside. So there's that square that I almost bungled up a moment ago. Okay, so square there, and then a couple more algebra things here. First, I'm going to combine everything on the right hand side. Looks a little bit messy, but actually it's not too bad. Let's see, this was actually an m1 right there. I'm going to have 1/2 times m1 as I combine this, m1, and then I'm going to have this actually negative is being taken care of by the square, so that negative does not survive. So I have plus, this is this plus here, let's see, m1 squared over m2 Why? Because m1 squared divided by m2 squared, but there's another m2 in the front. That's why I only have one mass 2 of the cannon itself in the denominator. And then I think I can close the parentheses, and I have a VF1 from the first, VF1 squared from the first term, and a VF1 squared from the second term, and I've taken care of everything. And now again, I move this a little bit up higher, and from that I then calculate the energy that I had calculated earlier, the 12.9 10 to the 6th. Of course, I could have written 1.29 times 10 to the 7, but I figure I write it in kind of like, so it kind of looks like megajoules. So 12.9 times 10 to the 6th joules times 2, so that's the 1/2 to the other side, and then divide by that parentheses, and that parentheses is 85 kilograms plus 85 kilograms squared divided by 5,800 kilograms of the cannon itself, and I hit enter, and I come up with 299,000, but I still have to take the square root of that, and I come up with a rounded 547. And because I have standard units throughout, kilograms, meters per second, and so on, joules, I come up also with standard units here. So meters, 547 meters per second. The cannonball is a little bit slower. It started out in a bolted case, it was 551 meters per second. So now you can say, well, hey, what's really the difference? Yeah, it's really tiny, about 1%. But I guess the people who fire the cannonball, if they want to do their ballistics calculations, it's important to them that they have a 1% difference.